Welcome, viewers, to the first installment of Global Specs exclusive interview series, What's Fueling Innovation 2024? And that's an exciting topic because we have a great guest on here today. Let's start off by talking a little bit about some background. More than half of the world's electricity is consumed by electromagnetic motors, which are only 60% efficient when integrated into real applications. And I can tell you firsthand, that is you're doing well at 60% in a lot of these motors. A large percentage of traditional motors are made from copper, and the highest performance machines rely on rare earth magnets that are almost entirely sourced from one country overseas. Another concerning point. Key component to a sustainable and low carbon future is finding new efficiencies in legacy technologies. That is at its heart what C-Motive does, and their innovative electrostatic motors offer modern technology to meet new engineering needs. Joining me to discuss this is Matt Maroon, CEO of C-Motive. Matt, of course, has 20 years experience in product management for engineering startups, with much of the experience in clean technologies focused on energy storage and distribution. C-Motive is a Wisconsin-based venture-backed organization that creates sustainable motor technologies that are 90% efficient with no rare earth magnets and low copper usage. Hi, Matt.
Hey there,
Welcome.
Dean. Thank you for having me. Excited to get started.
It is fantastic to have you here today. I have to tell you, I love what you guys are doing. It is a huge game changer. And I'm not one to use that word because I don't like it. You know, I think it's overused sometimes. But for me, I think this is one of those things.
Look, I'm biased, but I would agree with you. There are so many things in the world that we just take for granted and you never give it a second thought. And motors are certainly one of them. As you said, huge amount of the electricity in the world gets consumed by motors, and you're just like, well, it's a motor, but we believe there's a better way to do it.
Most people don't even know this has a motor in it.
Exactly.
It's an unbalanced motor. That's how you get it to vibrate. But that
Literally
it's
everywhere.
incredible. Yeah, they're everywhere. And sometimes we take it for granted, and we've just accepted the fact of the low efficiency rates that we have.
Yep.
So can you tell me about the origin of C-Motive and your role with the company?
Yeah, I'd love to. So I can't take any credit for the original idea or getting the company spun out. It was actually our two co-founders. So about 10 years ago, they were both getting their doctorates in electrical engineering from the University of Wisconsin-Madison, and they were looking for a big sort of problem to solve. One of our two co-founders, Dan Ludis, he had this idea that dated all the way back to Benjamin Franklin about, hey, what if you can make a motor that didn't use magnetic fields and used electrostatic fields? So that's kind of where the idea originally came from. Justin Reed, who is our chief technology officer, and Dan spun up this idea. They worked on it as part of their doctorate work. And then the company founded in Justin's extra bedroom in his apartment. And so it has gone from literally two guys in an extra bedroom to where we are today with, light manufacturing and a full lab space and a much bigger team than when the two of them started.
That's incredible. And a great success story. I love to hear those kinds of, how you just develop something. I think sometimes people think that you have to have a lot of money and you have to have everything else to go. Sometimes you just have to have a good idea, and that's all it takes.
The idea and just the willingness to try something different, right? There's something about being like early in your career and maybe a little naive about what it's going to take, right? But it's that sort of energy that you got to have in order to take something that that's really hard to develop and like actually get it out into the world.
So can you elaborate on C-Motive's motor technologies and how they're different from conventional electric motors?
Fundamentally, what makes us different is that we do not use magnetic fields. We use electric fields. So in your day-to-day life, an electric field you run across, if not daily, at least once a week, I would hope, when you put clothes in the dryer and you pull them out at the end, you get a pair of socks that stick together. The reason the socks stick together is because of the electric field that's built up on the surface. So we are using that same force just scaled up tens of thousands of times to convert electricity into mechanical power, but through the use of electric fields within the machine.
So what are some of the major disadvantages that you see in traditional conventional motors that are out there now? And
Yeah. I think anyone that's seen a motor at work or like even in your house, the one thing that we all know is that motors get hot, right? You never go up and put your hand on the motor because it gets hot. The reason it gets hot is because the way it is producing that magnetic field. Again, you're passing current through copper windings, and there is just resistive heating that happens. That is the primary efficiency loss in most traditional motors. If you want more torque out of your motor, if you want more power, you need to pass more current through the system. The more current you pass through the system, the more heat that you generate. You get into this, self-defeating mechanism. And so the limit that traditional motors have that we're addressing, so one, right off the bat, it's the energy efficiency. So we are operating at very low currents at medium voltages, which means we do not have that same heating issue that traditional motors have. The other limitation of traditional motors is that they are particularly good at high-speed applications. So think about the shaft spinning in a traditional motor is in the thousands of RPMs, usually anywhere 1,800, 3,000 RPM. But that's not, your ceiling fan is not running at 3,000 RPM. It needs to be geared down. And so you take a traditional motor and you need to attach a gearbox to it. You need to attach some sort of belt and pulley system in order to get to the application speed in the hundreds of RPMs. And that adds another set of efficiency losses. And so, when you let off saying, hey, traditional motors in their system are 60% efficient, it's because by the time you take that traditional motor that might be spec'd out at 85% efficiency, but you oversize it, you got to add thermal management, you add the gearbox to it. And so again, it's really the system level that we're addressing because our system is designed to deliver full torque and full efficiency from 0 to 500 RPMs. So we're getting rid of the gearbox, we're getting rid of the oversizing, we're getting rid of the active cooling. And so you can actually realize those levels of system efficiencies.
That's tremendous. So when you look at it in performance, how does that compare to traditional motors? What kind of efficiencies are you seeing now? I know you said 90%, but
yeah, so out of a motor, so let's take a simple example of just like an industrial fan, like a barn fan. So you walk around a manufacturing facility, there's fans that are plugged in the corner. Someone plugged them in 2 years ago. They've never been unplugged. No one thinks about them, but they're kind of critical for just moving air around. That traditional motor in there will have call it a 0.5 horsepower. Maybe it's a 1 horsepower motor. It's got a belt and pulley system to get the fan spinning at about 150 RPM. That thing is going to be 65% net efficiency. That same fan with the C-Motive direct drive motor on the back of it is going to be 93% efficient. And, again, they're manufacturing facility, you're going to have dozens of those fans just sprinkled throughout. Here in Wisconsin, with our industrial electricity rates where they're at, that fan costs about $800 a year. With the traditional motor, just plugged in and forget, you never think twice about it. Of that $800, well over 400 or 500 of it is just heat that you're throwing away through the efficiency losses. And so C-Motive comes in, you go from $800 to run that fan to under $300, and you're looking at, pretty quick payback periods, whether you've got a facility with 10 fans in it or, you're operating a shipping facility where maybe there's 2,000, 3,000, 4,000 motors. All of a sudden, those savings they aggregate up pretty quickly.
Changing the light bulbs in a facility, the savings is just incredible. I could tell you that firsthand, switching to LED lights on Christmas decorations that I did last year, huge change in my electric bill.
And we're talking about, these are not the sexiest of applications out there, right? No one thought, no one gets real excited about going to LED light bulbs, but why wouldn't you? Why would you not want to? A light bulb puts out obviously lumens. A motor sits there and spins. If we have a better, more efficient motor, that does everything else that traditional motor does, why would you not want to move to the one that is more efficient, that, domestic supply chain, all of the other aspects? So we think we can make a real big difference, for people's sustainability objectives, obviously for their operating costs and their utility bills, by just changing out the motors that likely no one has ever thought about before.
Gotcha. When we talk about net energy or waste savings, can you go into that a little bit more of what kind of whether it comes out in dollars or in watts or what kind of savings you're looking at?
Yeah, I think the easiest example is going back to that fan, just to start with. So that traditional motor in there with the gearbox or a belt and pulley system, $800 here in Wisconsin to run. If you're in Germany with 3x the amount of or 3x the price per kilowatt hour, you're talking about thousands of euros to just run that fan. So what we're talking about is, moving from at a system level, the motor gearbox, the traditional motor and gearbox at 65% net efficiency, to C-Motive direct drive at 90%. So you're talking about a 35% or 35-point gain in efficiency. It translates to about 65% savings, both in terms of the dollar amount, as well as, for those that are looking to hit Scope 2 carbon emission objectives, you're cutting down your emitted CO2 by 65% as well.
Can you elaborate on that a little bit for people that don't know what that category is?
On the carbon side?
Yeah.
Yeah. So a lot of companies have either made renewable energy commitments. More forward-looking companies are also saying, hey, not only are we going to add solar to our roof or, support wind farms, but we're also looking to track and reduce the amount of emitted carbon from our operations. And so there's Scope 1, Scope 2, and Scope 3 carbon emissions. Scope 2, the easiest way to think about it, those are the carbon emissions that come from, well, in this case, the electricity that you're using, right? Each kilowatt hour of electricity on the grid obviously has an associated, metric ton or whatever the number is of CO2 associated with it. So if you use less kilowatt hours, you are in effect generating less Scope 2 CO2. And so there's a ton of companies that have made those commitments to Wall Street that are now required to report on them. And, they've done the simple stuff like change out to LED light bulbs and, people put solar on their roof. They've done all the things. Again, motors are consuming 50, 60, maybe 70% of the electricity in these industrial facilities. It is a huge lever to use to not just save money, but also to meet those objectives that people have made to their shareholders.
Absolutely. I think you hit it on the head to me with just the heat element. When you have energy that isn't used, it's dissipated as heat. Which, whether it's unused because it wasn't transferred properly in the best manner and the most efficiency, that can be transferred into that energy converted into heat, which is anytime you feel that heat transfer, that's something is being wasted.
Yeah. There's a trickle down effect as well. So if you're operating a facility in Texas or in Florida, in August, it's already, God only knows what the temperature is, 90, 95 degrees Fahrenheit outside. If you've got a facility where you've got a couple thousand motors, you have to account for that in the sizing of your air conditioning system. And so not only are you paying for the energy that you're wasting, you're also double paying because now I got to get that heat out of the building as well. And so again, the efficiency comes in a lot of different forms, but I think one thing you realize is that it's not just one element. There is this trickle down effect that the further you go upstream, and motors are just so critical for so many different processes. If we can improve the efficiency there, it's going to trickle down across the entire supply chain.
Yeah, and you mentioned the inefficiencies of things of transferring energy through the gearbox and things like that. And can you tell me a little bit about how your motors perform better when you're talking about belt drives and gearboxes and things like that, routing it through those not the best efficient transfers of energy?
So the answer is we don't use a gearbox or we don't use belt drive systems. So the way our motor is set up, so instead of passing current through copper windings to create a magnetic field, what we do is we apply medium voltage, which in our case is anywhere from 2 to 4,000 volts, on the surface of printed circuit board plates. And so by applying the voltage on there, that's what creates the electric fields. And then by manipulating the electric fields on the stator, the rotor kind of moves, at the sort of speed and torque levels we want. This setup allows us to deliver all of our torque and 90+% efficient all the way down to 0 RPM. So you don't need to rev the motor up in order to get the torque out of it. What we're doing is we're delivering all of that torque all the way down at 0. So what that allows us to do is just run without the gearbox. We just get rid of it entirely. And so a lot of the applications we're focused on to start with, 1 to 3 horsepower motors, industrial settings. Think about things like conveyor belts and high volume, low speed fans, pumps, air compressors, industrial automation equipment, all of that stuff. Those things move in the hundreds of RPMs. And so we are specifically tailoring the motor to run natively direct drive on those applications.
Right. That helps a lot. What are some of the ideal applications that you have for a non-permanent magnet, low copper motor? What are the best applications for that?
Yeah, today we're going to start with that first product family for stationary industrial stuff. Your general use motor that you find in sort of any manufacturing facility. So, again, conveyors, automation equipment, pumps, vacuums, that sort of thing. This technology can go in a lot of different, I mean, one of the challenges we have as a very small startup company is that we can't chase every single bright, shiny object out there. As much as we would like to, we can't do it. So we're focused right now on that 1 to 3 horsepower industrial segment. As we, get into production with that, well, it'll allow us to turn our attention to other applications for bigger motors. So scaling up to 10, 20, 50, 100 horsepower machines for even bigger industrial applications. This machine has applicability in e-mobility as well. So probably not a Tesla Model 3 or, Porsche Taycan or something like that, but off-highway equipment that needs a lot of torque that's not moving very quickly. So agricultural equipment, construction equipment, really good application for this technology. And then beyond that, we think that we could even get into renewable generators. So think about huge wind turbines where you want to go direct drive to get rid of all the permanent magnets inside the motor. You want direct drive for the efficiency of it. We have designs on paper that we've modeled out where we have electrostatic motors that are 10 feet in diameter that can deliver megawatts of power out of them. Clearly, we're not building those today, but that's what we want to grow the team and grow the technology towards in the future.
Okay. And you're focused mainly on AC motors currently?
Yeah, we're also providing the drive. And so our drive is set up to work with all of the usual voltages that you would find inside a manufacturing facility. So we're providing the whole system, the motor, the drive, it plugs into our motors right now, just into the wall, 120 volt single phase, but set up for 480 volt 3-phase, just your general industrial sort of power ratings.
Gotcha. Overseas, are you guys focused on 50 hertz, 60 hertz?
Yeah, also very also capable of delivering that. Given the interest in Europe with energy efficiency and sustainability, that's a big market for us.
Yeah, I would imagine so.
Yeah.
Matt, we're just about out of time here, so I want to thank you, of course, for taking time today and offering a glimpse into the truly groundbreaking technology that you guys at C-Motive are bringing to us. So I want to thank you for your time.
Dean, I appreciate it. And of course, anyone that wants to find out more, go to our website. There's a bunch of explainer videos on our YouTube page. Plenty of ways to learn more about the technology. And of course, reach out if you've got interest or applications. We'd love to hear from people.
Fantastic, sir. For you viewers, look for future installments, of course, in our What's Fueling Innovation in 2024 interview series. Thank you, everybody.
Thanks.